Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at Chem Advantage. Here we've got a combustion analysis problem that involves empirical formulas. The experiment that's done is an important one. It goes back quite a ways. You take a sample that you want to find out about, typically an organic sample that has carbon and hydrogen in it, and you pump some oxygen in. You've got that sample weighed carefully here, and this refer to it as a boat. And then it burns in the oxygen, and you get water and carbon dioxide, which are collected in these absorbers, and the extra oxygen goes by, and we weigh the water and the carbon dioxide that's been collected in here. As I said, this has gone on for quite a while, and it's been a key in the understanding of compounds around us. In fact, let's go back to here, the father of chemistry, Antoine Lavoisier, who came up with the idea of combustion and elements and analyzed them. He was a spectacular chemist, and here's his apparatus where he burns something and then collects it in these two vials, and we're going back to 1789. Now, this method, taking a substance and breaking it apart, that's our combustion. We're separating a compound to find out about what its elements are. And this is von Liebig, Justik von Liebig. He is a great chemist, also a German chemist. In fact, this is his analysis method that is being used and his apparatus. Here you can see there's a little glass item that's used. The combustion products are collected in and weighed. And he would break apart all sorts of foods and organic compounds. And our formulas today are originated here in von Liebig's apparatus. In fact, the von Liebig also was one who was instrumental in determining the nutritional values in food. Our terms and ideas about nutrition and food are based on the chemistry of von Liebig. American Chem Society, one of the largest professional societies in the world, uses the apparatus, the combustion apparatus, where they bubbled and collected these gases to analyze substances. This is their logo. They've got the phoenix, where you burn this mythical creature and that will arise from its ashes. And from these ashes, we're able to analyze and find out about substances. Now, remember, we had Antoine Lavoisier doing this back in the late 1700s. And we're still using it today. Here's a very sophisticated combustion analysis device that will give you the carbon dioxide, hydrogen, and nitrogen. Rather than weighing the products, now they analyze them in terms of how much heat they conduct. And from that, they can give you a very accurate analysis of your carbon compounds very quickly, very accurately, and it's done routinely. Of course, your apparatus is going to cost in the order of tens of thousands of dollars. And here's an ad for one of them that shows how important combustion analysis is.
Analyzers. Ultra analyzers determine the carbon, hydrogen, nitrogen, oxygen, and sulfur content in all kinds of materials with the highest precision. They play a key role for the safety and quality of steel, copper, soils, food, fuels, or plastics, to name just a few. Our analyzers combust and fuse sample materials at up to 3,000 degrees centigrade and analyze the contents of the released gas in infrared or thermal conductivity cells.
This combustion analysis is critical if you want to know the formula of sugar or alcohol or even your body. This is sort of the starting spot where we can find out what the ratios of carbon and hydrogen are for the formula that we're going to be dealing with. I mean, DNA, sugar, carbohydrates, proteins, all here start with a formula. And that's why we're doing this problem, so you can see how it's done. And also, it's a really good review of understanding the principles of chemistry. So let's take care of this problem. This is the description that you've probably read already, where we burn the hydrocarbon and get water and carbon dioxide. That's the exhaust, and it's collected here. Some diorite and probably some sodium hydroxide. These things are weighed ahead of time, and we can find out by the difference in mass how much water and carbon dioxide was produced. They'll weigh this before the experiment and after the experiment, and the increase in mass will be the water and the CO2. Nowadays, they'll use infrared analysis or thermal absorption. This is the older technique, which was used for several centuries. And we'll use it to help us understand moles and grams. So we've got a sample with a mass of 133. Now I used milligrams. Typically they like to use small samples, and rather than writing down 0.136 grams, I've changed it to milligrams. In fact, in AP problems, if you've got small amounts of mass, you probably will want to change it to milligrams to make things a little bit easier for you. And we produced 122 milligrams of water and 447 milligrams of carbon dioxide. These two masses are greater than our organic compound because we've got oxygen added to the hydrogens and carbons. But that's not going to be a problem, because this is what we're going to do next. We're going to take those masses and find out their amounts in terms of chemistry, their moles, the numbers of molecules. Now, the first thing here we have is 122 milligrams of water. So we take that 122 milligrams of H2O, and we're going to convert that into amounts, moles, by using our standard grams to moles method, where we look up on a periodic table the mass of hydrogen and oxygen, and this is H2O, and by now you know that its molecular mass is 18.02 grams. We've done this often enough. This is one of the numbers you should remember. We use it often. You'll use it on the AP exam. And we'll grab our calculator, take the calculator, and put in our 122 milligrams, millis. This saves us putting a decimal point in, and we'll divide it by that 18.02. We could have gone to an extra significant digit, but let's just do it with 4 significant digits and find the moles, or I shouldn't say moles, because we cancel out the grams and have moles, but we still have the milli-unit. So we have, as an answer, millimoles, thousandths of a mole, 6.77. And again, if we would have had our regular numbers, we would have 0.006, which would have a pain in the neck to write, and writing 6.77 millimoles is a lot easier. That was our answer. Let me just pull that calculator up again, and naturally you're not going to write down 6.7702. Please don't do that. All you need is going to be 3 significant digits. If you're compulsive, you can take it out to 4. Well, that's our millimoles of water, H2O. Now, we aren't interested in water because of this oxygen. That's going to be a pain in the neck because it's got this extra oxygen in it, and there's 2 hydrogens. We need to know about the hydrogen in this H2O. Now, the grams are tough to mess with, but moles is very easy to deal with because we'll want to find the amounts of each element. H2O, there are 6.77 H2Os, and if you like to use dimensional analysis, we would take that 6.77 millimoles of H2O and multiply it by the conversion. There are 2 hydrogens, 2 H's for every 1 H2O. So this will give us the amount of hydrogen. We would just double this, and I'll get my calculator out and just go times 2. That's my amount of hydrogen. I now know the hydrogen amount. This is the H, the millimoles of H that were in our original sample. We've decomposed it. It says it has a CH formula, and now we find the H component of it using our calculator, atomic mass, moles, mole ratios. That's why this is such a popular question on exams in terms of empirical formulas, because it explains what's happening. This is grams to moles to formulas. That's just beautiful. Well, we've taken care of the hydrogen in our 136 milligram sample of our hydrocarbon. Now it's time to deal with the carbon dioxide, which is absorbed here or analyzed in our advanced analyzer. And we're going to do the same thing. We're going to change the milligrams into grams. So we have our 447 milligrams of carbon dioxide, which we'll enter in our calculator, 447, and divide that by our molar mass. And if you're doing dimensional analysis, you need to do that even though in this case you're probably so well acquainted with changing grams to moles you don't need that. But I'll divide that by the 44. Oh, by the way, remembering things. Yes, carbon dioxide is another one that you should remember, 44 grams per mole. It's used very, very often. So, I mean, you could look up the carbon 12 on the periodic table, then 2 oxygens, 32, and add them, but better off remembering 44.0. And our grams will cancel, and we'll have millimoles as our result. And there is our 10.2 millimoles of carbon dioxide. Now that's the CO2. We just need to deal with the carbons, and there's 1 carbon for every 1 CO2. So you don't have to do much at all. I don't even have a calculation for that. Just say, okay, this is easy. It's easier than the water. Had this been something other than carbon dioxide, we might have had to have a ratio, but we don't need that. I'm going to take that value, and I'm just going to store it as X, because I might want to be using that later on. In fact, indeed, I will. And that's now stored as X. I'll remember that. So we have our moles of hydrogen, H, and carbon. Remember, our original problem was to find out the question mark here and the question mark here, the lowest whole ratios that we would have in the formula. And we've pretty much gotten to that level because right now we can see that there is going to be in this formula that, let me get rid of this, it's distracting, and that there is going to be 13.5 millimoles of hydrogen compared to 10.2 millimoles of carbon. This formula is going to have more H's than C's. This right now should, I mean, you look at these numbers, they mean something. They're not just abstract numbers. This tells you about the ratio of carbon to hydrogen in whatever this compound is. Of course, you don't want to have a formula of 10.2 to 13.55 because anybody who's doing this experiment would probably have different millimole amounts. We're going to have to reduce these. So if we would have had 1 mole of carbon. Now, the typical instructions for an empirical formula is to take the lowest molar amount and divide that by itself, 10.2. So you've got 1. So we can say, okay, compared to carbon, what's the hydrogen? And so we would say our 13.5 millimoles of hydrogen to 10.2 millimoles of carbon. Calculator up. I'll take my 13.5. If I want, I'll do a 13.54. Just toss an extra digit in, divided by X, or I could have done divided by answer. And I will see that there's 1.33 times more hydrogen than oxygen in this formula. So I really have a formula. This would be valid for anybody doing this experiment. If they would have used 500 milligrams or 1/100th of a milligram of this original compound, they would find that this ratio, 1 mole of carbon to 1.33 moles of hydrogen, they're going to have 1/3 more hydrogen than they have carbon. This would be a formula, except, in fact, here I'll expose this so we've got that answer. I should have had that H to carbon ratio there. But in formulas, we like to have lowest whole number ratios. It's a little bit easier to see, and I agree with that. So I would take this value, which is done pretty accurately, and say if this were whole numbers without decimals, if I multiply this by 2, I would have 2 moles to 2.66 moles of hydrogen. Still not a whole number. But if I multiply by 3, I would have, I have to get my text out here. I'm going to say my carbon will now be 3. Oops, let me make that a subscript. And my hydrogen, 3 times 1.33 rounds up to 3.99, which will be, for all practical purposes, 4. And this makes a lot of sense. I like this. We've got C3. We have a little bit less carbon than we have hydrogen. There we have one-third more hydrogen. This is what we refer to as the empirical formula. So what is C3H4? What compound could that possibly be? Well, let's go to the internet and type in C3H4. What substances could have this formula? Well, here they're listed. One is cyclopropene, a interesting molecule. 1, 2, 3, very, very unstable because these carbons are being crushed together. It's explosive, actually, to some extent. But this would be a C3H4. But carbon is interesting in that you can do lots of things with it. So let me just move back. And the other possibility for C3H4 is this methylanthracene. And it has also called propine. And you can see here's its formula. H, we've got our 3 carbons. If you count the hydrogens, you see there's 4 of them. This is used in some types of torches. If you use MAP gas, this is used. And still, we can go back again. And here's another one, propadiene. Interesting looking molecule. Here we've got our 3 carbons and hydrogens. Organic compounds have got all these possibilities of the way in which you can put these carbon atoms together. So just with C3H4, we could have had 4 possibilities for these compounds. In this case, all of them would end up being a gas. But this was a solid, so we say, wait a second, did we this right? It's C3H4, but these substances were in a boat. They were a solid. And that's because this is the lowest possible formula. This is a ratio, well, actually, our lowest formula is 1 to 1.33. This C3H4 is just a whole number ratio, but it could have been a larger whole number ratio. This is the lowest whole number ratio, but if you look at C9H12, you could divide 9 by 3 and get 3, and 12 by 3 to get 4. So this is the same ratio. This has 1/3 more hydrogen than it has carbon. So if we had this substance, C9H12, we could have had the same result. Now let's do a quick lookup and see what those things could be. Done a look here, and here's a C9H12. In fact, actually there is a whole bunch of things that could be a C9H12. You go through each one of these and find out about what they would end up being. And some have some really interesting names. Just this one itself, the N-propylbenzene or phenylpropane is this compound. And again, we could check to see what its properties were, and that might help us. But we don't have to stop there because we could end up going to even higher ratio. I'll look at my possibilities. Here's another possibility, a 1824, where again, we'll have a 3 to 4 ratio. This one won't work because this is a 1 to 2. So if I go and type in that possibility, I would end up getting this substance, estrine, which would have that same ratio. So the empirical formula is sort of the starting point that you get. You know what the ratios are. You're going to need another experiment to find out which of these possibilities there are. So you should remember that there's a difference between the empirical formula, the lowest ratio, and the other possibilities, which these things could be. In fact, actually, this compound is not going to be C3H4 because we know it's a solid. And CH3H4 compounds, all of them are gases. So these others would be possibilities to look up. There's a number of other experiments that will help you determine the molar masses, and there'll be multiples of this original. So we've done our empirical formulas, a first step into really finding out about all these compounds. Now, one little postscript. You've done this problem and you're wondering, is it really right? Do I have the right answer? Well, there's a way of checking it out. You could say, I know the amount of hydrogen and I know the amount of carbon in terms of millimoles. If I find the gram amounts of these, they should add up to 136 milligrams. Well, let's check and see if it does. I'll get my calculator. I'll clear it. And I'll take my hydrogen, my 13.5 millimoles, and multiply by the atomic mass of just hydrogen, 1.008. I remembered that. It's used often enough. That's going to be the mass. In this 136 milligrams, there's 13.6 milligrams of hydrogen, the light atom. And I'm going to add to that my 10.02, which was my carbon that I remembered, which has an atomic weight of 12.01, another common element to be used. And we'll see if we get this 136. Let's see if you're going to be right. There we are. It rounds off to 135.6 for our third significant digit. Our mass of carbon and mass of hydrogen are the mass of that sample that we had in that weighing boat that gets incinerated and changed into carbon dioxide and water that we changed into amounts of hydrogen and carbon. Empirical formulas. Beautiful. The numbers work out, they make sense, and we find out about the world around us using a calculator and a match burning things. That's great chemistry. Love it.